All right, ladies and gentlemen, we're going to take a look at our last transformation, and that is rotation. So we're going to identify a rotation and what rotational symmetry is. Once again, we're not following along, so this is lesson 11.8. So we're jumping around in the note-taking guide. So what page you are on, you think I would learn to type this in there. 11.8 is the last lesson in your note-taking guide. And so we're going to take a look here at page 283. So if you need to pause and get turned to page 283. We've got some vocab we want to go through first. Rotation. It's just a transformation that turns a figure about a fixed point. So we're going to have a fixed point and we're going to turn around it. So if you think of like a carousel is a rotation because there's the middle post and everything turns around on that. The center of rotation is the fixed point, so whatever we're rotating around. The angle of rotation is the angle drawn between a figure and its image that uses the center of rotation as its vertex. And so where you really see this is not necessarily drawn in, but we're going to say rotate 90 degrees. That 90 degrees, so if you see rotate 90 degrees, this 90 degrees is your angle of rotation. And then rotational symmetry, similar to what we talked about with reflectional symmetry, is when a figure can be mapped onto itself with a rotation of 180 degrees or less. So once we turn more than 180 degrees, we're saying that we're back to a similar rotation. All right, so let's take a look at what this is. So we want to say, does a figure have rotational symmetry? Can I rotate it and have it mapped right onto itself so it looks like the exact same figure I have? And that's what it means to map onto itself. You want to look exactly like the original. So we can rotate anything, but to have rotational symmetry, you have to look exactly like itself. So if we look at the rectangle, yes, a rectangle can have rotational symmetry because it can be mapped onto itself by a clockwise or counter clockwise rotation of 180 degrees about its center. Okay, so if we look at what that diagram is saying, all right, here's our center, and this is 0 degrees. We haven't moved at all. If we look at the next one, if we draw in from that center a 180 degree angle, a straight line, and we rotate around that, we rotate 180 degrees, we are back to the same figure we had before. All right? So that's what it means to have rotational symmetry. For the second one, no, because the trapezoid does not have. Right? It's not what I would call a symmetric figure. There's not a line of symmetry. So if there's no lines of symmetry, then it's difficult to have a rotational symmetry to it. All right, so your follow-up here. Figures A, B, and C are images of the original figure. Tell which figure shows the rotation described. So I need to go 90 degrees clockwise. 90 degrees is 1/4 of a circle. So if you think of a clock, so we're going clockwise, you want to turn this to 3 o'clock. So which of these looks like my R has now turned to 3 o'clock? Well, why, of course, figure C. Now, 180 degrees clockwise is just half of a circle. And so we need to show up at 6 o'clock. All right. So if we look at 6 o'clock, if I turn to 6 o'clock, I'm going to be at letter or figure A. You are going to do these now, and we will check in class. We'll go through those. That'll be part of what we do during the warm-up, or would I come around and check with you? All right. Does the figure have rotational symmetry? All right. So we want to take a look at and decide, does the figure have rotational symmetry? Can I turn it so that it maps onto itself? Well, if I look, I can't turn this in any direction less than 180 degrees and not end up looking differently. So for the trapezoid, that is no. If we were to take, I guess if we took a look at this, if I try and put in a trapezoid, let's see. We do have a trapezoid right here. So let's put that trapezoid in. If we take and turn this, as we look, it looks completely different. Let's put this up here. Let's try and see if we can get these to match up. Pretty stinking close. So if we rotate this, it's never looking exactly the same in any turn. So we don't have our trapezoid. So that's no. For the parallelogram, let me get a parallelogram here. Let's see which shape looks like our parallelogram. This one looks closest to our parallelogram. So if we take our parallelogram, turn it sideways, we'll flip it over, flip up or down. That looks like it's a little bit more close to fitting what we have here. All right, so if we rotate it, we rotate around. Look, I go 180 degrees and I'm back looking like the same original figure. So this is, yes, describe the rotation. It's 180 degrees. So we're picturing this thing turning, and if I turn it halfway around the circle, I get the exact same figure. Number 3, I want to do in class. And we'll check these together. All right, if we take a look at what's going on, we have example 3, reflections in the coordinate plane. We are going to skip that because it has us working with protractors and straight edges, and so we're not going to do that one right now. But what we want to do is the rotations in the coordinate plane, example 3, and we're going to skip that, but we will end up doing that one in class. All right, so that's it for today. Have a good evening.